Can everyone hear me? Higher. Is this good? Okay. Yes, definitely change of pace, as this will be about abstract allocators. So, hi everybody. I am Thomas Gilray, and my co-authors on this were Michael Adams and Matthew Might. And I'm going to be talking about our paper, Allocation Characterizes Polyvariance, a unified methodology for polyvariant control flow analysis. So in the last 35 years now that this 5-syllable word has been in use, a wide variety of different polyvariant strategies for flow analysis have been published in the literature. And a pattern that we might identify across a good number of these different papers is that the authors will, at the top of the paper, give a high-level, informal, descriptive definition for what is meant by polyvariance in general, and then in the body of the paper, they'll formalize a particular instance of a polyvariant flow analysis, or sort of a highly constrained small set of different flow analyses. But what we're interested in doing is capturing a broad notion of polyvariance and its entire design space. And how we do this is by producing a parametric framework for analysis where we can plug in different abstract allocation functions. And the design space, in this framework, the design space of these different abstract allocation functions end up characterizing the different styles of polyvariance that we can capture in our framework. So particular abstract allocation functions, or small sets of abstract allocation functions, are able to recapitulate classic styles of polyvariant flow analysis, like call sensitivity, object sensitivity, argument sensitivity, and so forth. And not only can we unify a design space of these polyvariant techniques, but we can also generalize and extend them to new forms of polyvariance, variations on these, general strategies for mixing and matching and combining them. And we even notice that more fundamental ways of re-architecting a flow analysis and more broad trade-offs, which I'll mention at the end, are also, which had never previously been called polyvariant, are also capturable in this design space. So it ends up being much broader than we had anticipated. But before I get into specifically what this design space looks like and how we formulate our framework, let me first illustrate polyvariance by talking about call sensitivity, which is the first technique that was given this title. So let's consider a max function, which takes two parameters, a and b, and a call site for our max function with constants 1 and 2. Well, in a monovariant flow analysis, what we end up doing is tracking a single flow set. So this means a collection of possible reaching flows to some point in the program for each syntactically distinct variable in our program. And so here, because a and b are distinct variables, we'll end up keeping these two constants separate in our flow analysis. But when we encounter another call site to max, let's say on hi and world, well, these two new constants will flow into the same two flow sets because we only have a number of flow sets equal to the number of variables in our program. So here, one will become conflated with hi, and wherever else it may flow in the program, we won't be able to know that hi couldn't flow there as well. So we've lost precision. And polyvariant techniques are basically those which create a greater preponderance of different distinct flow sets, add greater complexity in our analysis, but allow for more precision. So in the case of call sensitivity, we keep flow sets distinct both to syntactic program variables, but also to some finite call history. And so here, because we have two different call sites and also two different variables, we get 4 distinct flow sets with all 4 of these constants kept separate. So the idea here is that we've increased the complexity of our analysis, but in a way which allows us to increase the potential to increase the precision of the analysis as well. And often it works this way, but it's tricky to know when these things are going to work in different programs. And basically, different styles of polyvariance are like different heuristics for guiding us to a certain kind of trade-off between precision and complexity in a flow analysis. They're gambits that if we add a certain kind of complexity in our analysis, that we'll get a disproportionately high increase in precision as a result. So the idea here in our call-sensitive analysis is that the two flow sets on the left are specific, not just to their variables, but also to this first call site to max, and the same for the second two for the second call site. So the big picture is that we're going to be building on top of a very standard state machine-based abstract interpretation, that of abstracting abstract machines, and we're going to extend this with a very general notion of polyvariance. And we're going to do this with two parameters, an abstract allocator and an instrumentation. The abstract allocator is like a normal allocator. It's a function that gives us back addresses, but it might give us back a finite set of addresses and give us back the same address multiple times, whereas a concrete allocator will always give us back fresh addresses. And an instrumentation is basically an arbitrary dynamic analysis of our static analysis, which tracks additional information. So in this talk, I'm going to give you sort of three key ideas from the paper. The first is that abstract allocation determines the polyvariance of a flow analysis. The second is that an instrumentation encodes context information and basically lets us argue that we can be complete for our notion of polyvariance. And then we use the a posteriori soundness theorem from Might, Manolius, v. M. Kai, 2009, in order to prove that this is always safe, that no matter how we tune these two parameters to our framework, that we're always going to get a sound, correct flow analysis. So I'm going to talk about abstracting abstract machines, which is a systematic way to take a concrete, exact semantics for a program, and then systematically turn it into an abstract semantics for the program, which can be the basis for our static analysis. And this gives us a store passing style transformation, which exposes an abstract allocation function. And then I'll talk about how we can encode different styles of polyvariance as different abstract allocators. And I'll talk about what how instrumentation is sort of important here to enable more different kinds of polyvariance. Some can't be captured with just an allocation function alone. And then I'll talk about the a posteriori soundness theorem and give you a sense of why it is that we can always we can tune these parameters however we want, and it'll always lead to a safe sound analysis. So let's consider an abstract machine for a very simple CPS functional language with a control expression and a binding environment and a value store, which is like a model of the heap. And so, for example, we might have a let form or a direct application of a lambda, and a binding environment, which is going to map free variables in this expression to addresses for those variables, and then a value store, which is going to map addresses to specific values. And then we're going to pair this with a transition function, which is going to consume a state like this, and then it'll give us back, it'll either halt or it'll give us back a successor state, an immediate successor. So we're going to move inside the lambda or the let form, and then we're going to generate a fresh address, which we map x to, and then we map that fresh address to the square root of 9, 3. And we can also distinguish this generating of a fresh address as a concrete allocation function, which takes information about this transition, looks inside it, and makes sure it's generating us a fresh address, and that's what it hands back to us. And with this preparation, we'll be able to then produce an approximating abstract allocation function, which might give us back the same address multiple times and reuse addresses. So now, armed with a concrete semantics like this, we can evaluate our program by wrapping it up in an initial state and then iterating our transfer function on it. And if our program wouldn't terminate, then this process might not either. But crucially, we're specifying a specific computable or incomputable fixed point, which we can then approximate with the process of abstract interpretation. So AEM basically says, well, now what we've done, if we structure our analysis this way, or structure our semantics this way, so we have an unbounded set of concrete addresses. But we want a finite set of abstract addresses so that we can finitize our semantics. So we can turn this into a finite set of abstract addresses and then propagate that abstraction up to get a finite semantics overall. And so what we get basically is a mapping, or a Galois connection, an abstraction map, which tells us how these concrete addresses are partitioned into abstract addresses. And as you might already have a sense here, there's a wide variety of different ways that we can do this. And that brings us basically the first key idea, which is that abstraction maps for addresses determine the polyvariance of our analysis. This tells us how we're merging and differentiating flow sets in our abstract store and what the polyvariance of our analysis is going to be. And the set of abstract addresses we produce is the image of our allocation function. It's the output of the allocation function. And so the size of this set of abstract addresses and in what order we produce them and when we're producing them, that is basically determining this abstraction map, which in turn determines our polyvariance. And I'll give you an illustration later, which will, I think, make this a little bit more clear. But that's the basic idea. So now, with an abstraction map for addresses, we can lift this to an abstraction map for program states as a whole. And so for a particular concrete program state, we can determine its most precise abstract representative, which would concretize to some set, maybe an infinite set of different concrete program states that it stands in for. And in our abstract program state domain, we're going to have a rich lattice of varying degrees of precision that we can express. So the major change, or two sort of simultaneous changes that we get in our abstract machine, is basically relationality, our compression of our concrete address set to a finite abstract address set gives us simultaneously relationality in the abstract store. So now multiple closures can become conflated at a specific abstract address. And also non-determinism or relationality in our abstract transitions. So if we have an address for a variable in call position like this with two possible closures, then to soundly simulate this point in the program, we have to have a branch in a fork in our abstract transition graph. So we need to have two successor abstract states where this could go, two possible callees for this function. So now, with an abstract semantics like this, we can perform our flow analysis by taking our initial state and abstracting it, and then iterating our abstract transition relation now on it. And if we have a finite number of addresses, then we're gonna reach a closed finite abstract transition graph after some finite number of steps. And the idea here is that for this to be a sound simulation of our concrete execution, if we were to line up our concrete execution, this would necessarily map onto some path through our abstract transition graph. And this simulation property for our static analysis as a whole is induced by a similar simulation property for transitions themselves, which basically says if we have a concrete transition and an abstract antecedent, then we might have some number of spurious abstract transitions, but we're going to have at least one sound one. And we could lose as much precision as we want on that sound abstract transition without it impacting the soundness of our analysis. So now let's talk about how we can encode different kinds of polyvariants as specific allocation functions. And to start, we'll sketch out sort of the extremities of this design space. So here's an abstract allocation function, and we can give it the variable that we're binding, and then a bunch of other information about the current abstract transition that we're making. And I'll talk more about what kind of information we might include in just a second, but it's not important for right now. So the least polyvariant allocator, or what we could call the univariant allocator, will produce a single top abstract address that stands in for all concrete addresses. And so essentially we're creating an analysis that only has one big flow set for all the reachable values in the program. And this would really be quite imprecise and probably only useful for a cheap dead code eliminator or something like that. But the monovariant analysis that we saw earlier is a little bit more precise and basically emits an abstract address specific to each program variable that it encounters. So at the end of the analysis, we're only going to have a flow set for each syntactic variable in our program. And interestingly, we can also capture concrete allocation in this same parametric framework. So if we create an abstract allocator, which just like a concrete allocator would give us back a fresh address in every case, then we can also simulate concrete evaluation within the same framework. So let's look at another example. This is the Cartesian product algorithm of Augustine. And the kind of imprecision that this tries to address can be illustrated well with our max example from before. So if we have a monovariant analysis or a zero CFA type of analysis, or if we have a call-sensitive analysis, but with some amount of obfuscating eta expansion around max, then we're going to end up with, say, in a type recovery analysis, int or string for both A and B. And from a context agnostic perspective, this is not imprecise. I mean, both of those are valid flows. But CPA addresses the imprecision that this sort of implies that we could have both an int and a string passed into max at the same time, which isn't actually possible. So CPA, the idea behind CPA is basically to explicitly enumerate all these tuples of dynamic types instead of allowing these spurious ones to be implied. And we can actually do this as well. And what we're going to do is we're going to include all the other information that we have in our abstract transition. So the call site with all of its arguments, its environment, the entry point of the function that we're transitioning to, all the information that's calculated before the allocation function needs to be invoked. And we'll just give it to the allocation function and say, go ahead and look at this information. But all we actually need are these arguments. And basically, we can take these arguments and we can either come up with a dynamic type if we're doing that kind of an analysis, or we can come up with the syntactic lambda if we want. We can't generate the whole closure that would lead to unboundedness, but we can generate the lambdas if we want, and we can take a tuple of this information and just embed that in the address. And so this will end up simulating a kind of argument-sensitive or CPA style of polyvariance. And likewise, we can also give a simple definition for one call sensitivity. So we have the last call site right here, And basically, we just create an address which is unique to X, but also to this last call site. But what happens if we want a 2-call sensitive analysis or 3-call sensitive analysis? Well, here we run into a problem because we just don't have that information. So if our allocator is a pure function, there's no way for it to track this information on the side. There's no way for it to come up with this information. We can't encode this style of polyvariance. So what we do is we instrument our analysis to add this information. So we add a 4th component to our program states, which tracks a history of, say, the 2 previous call sites that we reached, call 1 and call 2. And let's say we're at a call site, call 0. Well, then across this transition, we maintain our tracking of the previous 2 call sites by pushing call 0 onto the front of this list of previous call sites, and we drop 2. So this is how we can instrument our analysis with a kind of dynamic analysis of what's going on in the analysis in terms of call histories. And then if this information is encoded as I and also handed to the allocator along with all the other information, then we can include it in addresses to instantiate different styles of call sensitivity. So certain kinds of polyvariants require extra information basically to empower the allocator to differentiate addresses in a certain way. And this brings us to sort of the second key idea of the paper, which is that even though abstract allocators are always the proximate cause of polyvariance in a particular flow analysis in our framework, most interesting kinds of polyvariance require extra information. So we allow an arbitrary instrumentation or arbitrary dynamic analysis of our flow analysis as another parameter that can be used to empower these kinds of allocators and these kinds of polyvariants. So one more quick example, and I won't give, it's a little bit more complicated, so I won't give what's in the paper, but there's more details in the paper. We can do object sensitivity, and this is a good example of a more sophisticated kind of instrumentation. This tracks a history of allocation points for objects. So the allocation point of an object, or for 2 object sensitive, the allocation point of an object and the allocation point of the object which allocated it, and so on and so forth. And then it differentiates flows according to that when, according to the receiving object for a method, when a method is called. And so for object-oriented languages like Java, this is great because you can often see through dynamic dispatch and things like that. And in our framework, we can capture this by including an instrumentation which tracks a history of allocation points for all of the abstract objects. So it's basically a mapping from abstract objects in our analysis to the allocation histories for those objects, and then we can use these inside the allocation of addresses. So this brings us to the third key idea, which is basically a question that you might be asking yourself. Is this cheating or sort of trivial in a sense? Are we saying, well, you can do anything you want with an instrumentation, and therefore you can do anything you want? And how do we know that these things are always sound? How do we know that these analyses are always correct? And both of these are addressed by the a posteriori soundness process of Might and Manolius. And basically, there are 2 main styles for showing the soundness of an analysis like this. Either we produce a full specification or Galois connection, and then we directly calculate an analysis for it, or we produce both a specification and we produce an analysis, and then we justify them as sound after the fact, or a verification approach. And these are issues that David Dureus talked about more yesterday. But in both of these 2 styles, we end up having to produce a full Galois connection or a full specification for our analysis ahead of time. And in the a posteriori soundness process, we actually are only able to produce a full Galois connection after a specific analysis has run. That's kind of what makes it really interesting. So we can only produce our abstraction map for addresses, in our case, after a specific analysis is run, after we know what the behavior of the abstract allocator was. So I'll try to illustrate how this works and why a concrete allocator as a component of our semantics uniquely allows this process. So imagine that this is our concrete execution of our program. And in the a posteriori soundness paper, what's called a dependent simulation of it, basically the portion of our abstract path which would correspond to this, assuming we have the right abstraction map for addresses. And then along some of these concrete transitions, we're allocating a concrete address. Well, the idea here is that whatever abstract allocator we provide, we're generating addresses which then tell us incrementally, step by step, what we should be adding to the abstraction map for addresses. So here, if we generate an abstract address A1, we're saying the mapping for concrete addresses to abstract addresses, the abstraction map, should have a pair A1 to A1 hat, right? And so in each of these cases, we have the choice of producing a new address, or we have the choice of reproducing an old address. And again, we can produce a new address, and then we can produce an old address again. And what we do basically, what we're doing basically is we're building up a partitioning of concrete addresses into abstract addresses. And I think a good way of illustrating why this is always possible for concrete allocation is to ask, what would be a counterexample? How would it be possible to produce an inconsistent abstraction map for addresses? Well, we would have to produce a concrete address which could appear in two of these partitions simultaneously. And that's only possible if we're using a concrete allocator which will produce the same concrete address twice, and then we have an abstract allocator which maps that same address to two different abstract addresses. And so because it's essentially a central characteristic of a concrete allocator that it always produces fresh addresses, this is possible. So we always get a sound analysis no matter how we tune our allocation. And as opposed to the two approaches that I mentioned before, this is fully ad hoc. We don't have to design a verification, and we don't have to know exactly how our analysis behave. We can be completely dynamic, and we also know that we're always going to have a guarantee of soundness. So there's a lot more information in the paper. We talk about different styles of polyvariance, and we explain more fully how we capture this in a total design space. We resolve some old ambiguities and give some examples. We also generalize this and talk about new forms of polyvariance, including sensitivity to values in the store and other kinds of things like this. So the main takeaways that I want you to the main things I want you to take away from this are that this is a general idea, not specific to our exact formulation, and it takes a couple of main ingredients. You need a store passing style which exposes a tunable address space, in which case an abstract allocator can determine the polyvariance of your flow analysis. An instrumentation allows completeness for polyvariance, and we know that this is always safe because of the special property of concrete allocation and the a posteriori soundness theorem, which will permit all allocators. So we can even use unsound instrumentations of our analysis, or sort of fuzzy heuristics as our instrumentation of our analysis to guide the allocation of addresses. And that unsoundness in our instrumentation still cannot lead to unsoundness in our flow analysis. That's kind of the punchline. And we should wonder what else can be expressed this way, what else is in this design space, and is it possible that with this framework we can produce more adaptive forms of polyvariance in the future. Thank you very much, and I want to acknowledge my co-authors on this again, Michael Adams and Matthew Might, and I'll be happy to take your questions.
So we have time probably for one or two quick questions.
Takayuki from Riken. So this technique should be very useful in terms of program efficiency. So can we push this forward and map all the address to the same address so that we can transform program using immutable data structure to that using mutable structure?
Can you say your point about mutable versus immutable structures?
Yeah, immutable. Can you transform the program that using immutable data structure to that using the mutable structure? So we are using constant amount of memory. We are not allocating altogether.
Yeah, I mean, I think it should be possible to do things like distinguish between mutable and immutable data and how the allocation is performed. I'm not sure I have a great sense of exactly what kind of a heuristic there would give you a good trade-off between precision and complexity. But I think being able to use these kinds of heuristics to find a better trade-off is what we want to do. And I think that sounds like a very interesting idea.
Thank you.
So just take one more and then I have to.
Gleb, very good at Google. It seems like there is some connection between extending the abstract allocator function with instrumentation. It seems to be similar to making the abstract allocator function into monadic computation. Is there any parallels? Are there any parallels here? Do you think so?
So I think I think it would be possible to capture the way that the store is handled as a monad, and then the allocation behavior could be sort of encapsulated that way. And there's some there's a paper that I think is in a draft form by also David Dreas and Nick Labeck and others from Maryland, which addresses this.